Hello, ladies and gentlemen. This lecture was presented at the Isranalytica 2023 conference and exhibition, one of the most important scientific events in Israel in analytical chemistry. When we drink our glass of water, we assume that this water won't harm us. As an analytical chemist, I can assure you that tap water in Israel is of very good quality. However, we always strive for improvement, and even in something that is good, we look for ways to make it better. Thanks to increasing use of desalinated water in Israel, we have almost solved the country's water crisis. However, at least one problem remains: a lack of certain minerals in the desalinated water that we are drinking more and more today. Several years ago at this conference, our group presented the results of a survey of the magnesium content of tap water and found a significant decrease in its concentration over the past 10 years. We also warned the public that household water filtration can reduce the concentration of beneficial elements in water. Today, I'd like to talk to you about total iodine determination using ICP-MS, the challenges of this analysis, how we solved some problems, and what we found regarding the iodine status of our drinking water. For the next half hour, our agenda is as follows. We will discuss the issue of iodine deficiency under the condition of heavy reliance of desalinated water. We will examine the challenges of iodine determination using ICP-MS. I will share with you how we solved one of the analytical problems in our laboratory. And once we developed a reliable method, we analyzed bottled water from the supermarket and conducted a survey of tap water from faucets across the country. We will review the results and discuss any conclusions that can be drawn. Iodine is element number 53 in the halogen group. It has only one stable isotope, I-127, with an abundance of 100%. Iodine is a relatively rare element in the Earth crust, but it is essential for good health at all stages of human life. It occurs naturally in water in the form of the iodide anion, I-. There is no standard for the minimum necessary concentration of iodine in drinking water, but according to scientific literature, a risk-reducing concentration in drinking water is around from 5 to 50 micrograms per liter. The recommended dietary allowance for most adults is 150 microgram per day per person. The issue of iodine deficiency in Israel is the major concern today. Unfortunately, there is no iodine prophylaxis provided by the state, but multiple national surveys in recent years have shown that most Israelis, both adults and children, are not getting enough iodine. Most of the iodine we consume comes from food sources like dairy products and eggs. In Israel, about 16% of our iodine intake comes from drinking water, and I would say came because 16% is too old results, too old data obtained from previous researches that were performed before intensive desalination water use. So the questions we'll be addressing today are: how much iodine is present in drinking water we consume, and how can we measure these concentrations? Desalination of seawater is a growing industry worldwide, especially in the Middle East, which is the most water-scarce region in the world. Currently, desalination plants in Israel provide about 80% of the potable water used in households. Some cities and settlements are almost completely reliant on desalinated water, while others are mostly supplied by water from Kinneret Lake and local wells. Desalination water produced from seawater using reverse osmosis technology is actually distillate water and cannot be used as drinking water without remineralization. On this slide, you can see the approximate parameters that desalinated water should meet. Note that desalinated water, which is considered to be of good quality, has very low concentrations, if any, of magnesium and iodine, and iodine is not even listed among the parameters. Ladies and gentlemen, if you take a look on this map, you will see the locations of the largest desalination plants built in Israel. According to the scientific literature, the iodine concentration in tap water in the Ashkelon district in 2003, before the Ashkelon plant started operating, was 52 micrograms per liter. But 5 years later, after the plant was in operation, this concentration decreased to 27 micrograms per liter. In the most recent article we found, the evaluation of iodine content in Israeli tap water was from 4 to 20 micrograms per liter. So let's take a look at what we found, but first let's discuss the details of the method we used to determine the iodine content in drinking water. As I mentioned earlier, iodine in water mostly occurs as iodide, but other species such as iodate, free iodine, and organic iodides may also be present. On this slide, you can see the chemical equation that connects these species, and you will notice that the volatility of iodine is strongly dependent on pH. In acidic media, which is most suitable for ICP analysis, iodine becomes volatile, but it is much less volatile in basic media, in alkaline media. It's also important to keep in mind the memory effect, which is very strong for iodine in acidic media. The iodine tends to stick to the glass parts of the sample introduction system, and it is difficult to wash off. There are several methods for iodine determination, each with its own advantages and disadvantages. The spectrometric technique, specifically ICP-MS, has excellent sensitivity and high throughput. However, the disadvantages of this method include the relatively high cost of the equipment and challenges with method development. As I previously mentioned, it is better to determine iodine in basic media, which is not so common for ICP-MS. But we used a 2% ammonia solution as a matrix and achieved good sensitivity with no matrix effect. We developed a method for iodine determination in mineral water samples with an addition of ammonia to bring the pH to above 10. And it worked well until we encountered nebulizer clogging. You may know that the nebulizer, which converts the sample solution to the mist, is a very sensitive part of the sample introduction system and prone to blockage. If we experience a blockage, it means that there are insoluble particles present in our water sample. I'm confident that you already understood what our problem was, but it took some time for us to identify the issue when it arose. And of course, our problem was carbonate precipitation at pH above 10, as shown in this equation here. This process is not too fast, so you may be able to successfully measure samples with a high pH, but if you leave the sample treated with ammonia overnight or for a full day, you will definitely block your nebulizer. And again, I'm sure you already know the solution for this problem, and of course it is adding the chelating agent to our solution, to our basic alkaline matrix. We used 0.1% EDTA, which was sufficient for most of the concentrations of calcium and magnesium that we measured. We evaluated the accuracy of our method by measuring a series of spiked samples. We used several bottled waters with different concentrations, but I'm not permitted to mention specific brand names according to the rules of our conference. As you can see, the spike recovery was consistently close to 100%. We did not have a certified reference material for water with a known iodine concentration, so we used a plant material certified reference material with the information value of the iodine content. We performed a closed acid digestion of the sample, then diluted the cooled acidic solution with our basic metrics and achieved very good recovery. To evaluate the precision of our method, we ran the same sample of bottled water, which contained about 10 ppb of iodine 10 times, and obtained a coefficient of variation of 1%, which is very good. So we tested a few different elements as internal standards for iodine determination, and we found that germanium and cesium worked the best. We used a concentration of 20 micrograms per liter. Cesium provided high intensity and slightly better stability throughout the workday compared to germanium. Plus, the cesium isotope we used has an abundance that's similar to the iodine isotope at 100%. However, when we compared the same results that were corrected using cesium and germanium as internal standards, we saw a strong correlation between the two datasets, and there was no significant difference between the absolute concentration values. So you can choose to use either cesium or germanium as an internal standard for iodine, whichever one you have on hand in your laboratory. So, to test our hypothesis about the effect of EDTA on the solubility of carbonates at high pH, we conducted the following experiment. First, we used ICP-MS to analyze 8 bottled waters and a tap water sample for the calcium and magnesium content, following the usual procedure in our lab, which involved acidifying the samples with 1% nitric acid. Then we created 2 sets of the same samples. One set was diluted twice with 2% ammonia solution, which we called the A matrix, and the other set was diluted twice with an ammonia plus EDTA matrix, which we called the E matrix. We incubated the A and E matrix samples at room temperature overnight, then measured the calcium and magnesium concentration using ICP-MS. And you can see the results on this slide. The red columns show the calcium content in the ammonia-only matrix, and they are significantly lower than the original content in the water, which is shown in blue. But the green columns, which represent the EDTA matrix, show almost the same concentrations as the water samples, except maybe for this one sample, which was a heavily mineralized bottled water. When we add EDTA to keep our calcium soluble, we should use a 1:1 molar ratio, but that wasn't the case for this specific sample. We got similar results for magnesium content as well. We found a way to keep our calcium and magnesium salt soluble at high pH, and now we need to ensure that this treatment does not affect the iodine in our samples. We compared the iodine content in matrices A and E from the previously described experiment for 3 bottled water, and t-test did not find any difference. We also evaluated the stability of total iodine in water samples under different storage conditions. The gray columns show the iodine concentration in waters analyzed immediately after being delivered to the laboratory. The blue columns show the sample stored for 2 weeks in the fridge at 4 degrees, as is, without any pH change, and the green columns show the same sample stored under normal laboratory condition at room temperature. Iodine concentration was analyzed in all samples using a two-fold dilution with E matrix, and there was no significant difference among the 3 groups of samples. We can conclude that you can store your water samples for at least 2 weeks in the fridge or just in the lab, and your iodine concentration will be okay. These are the results of our improved method applied to different bottled water brands found in Israeli supermarkets, as well as tap water taken from our lab faucet. As you can see, different brands differ in the iodine content, but the average value is similar to that found by other researchers many years ago. So, bottled water may or may not be an important source of iodine for you, depending on which brand you drink and if you drink this water at all. But we all use tap water, whether it's for drinking or cooking. It's cheaper and more readily available than bottled water, and in Israel the tap water is of very good quality. So, what is the iodine content of our tap water? We collected samples from different parts of Israel, from small towns and big cities, and all of these samples were from the faucets of end consumers. When we measured the total iodine concentration in these samples and ranked them from lowest to highest, we got 4 separate groups that differed significantly in the iodine content. The range of median iodine concentrations for all groups was from 0.3 to 12.3 ppb. This is the iodine level of our tap water. On this slide, you can see the distribution of our sampling points on the map of Israel. Let's zoom it and see that the points in groups C and D, which have the highest iodine content, are mostly in the north of the country, with an exception of 1 point at the Dead Sea. And the points in groups A and B are mostly in big cities in the central and southern part of country. Together with tap water, we analyzed a group of samples from the 3 largest desalination plants in Israel, Hadera, Palmachim, and Ashkelon. The iodine content in the post-treated desalinated water that is sent by these plants to the city's water network is extremely low. However, there is a significant difference among the 3 plants. Nonetheless, even the highest concentration is less than 1 microgram per liter. We also analyzed several samples of natural water to evaluate the level of iodine in the sources of our tap water. As you can see, the highest iodine concentration was found in seawater, and the process of desalination reduces the iodine content from 66 to less than 1 microgram per liter. Kinneret Lake water, which is one of the main sources of water in the national water carrier of Israel, at least in the recent past, provides us with 15 micrograms per liter. In river water, as you can see, the iodine content can vary significantly from river to river, and the same is true for water from local wells, which is also an important source from some cities in Israel. So, what are the differences among the analyzed waters besides the iodine content? Let's evaluate other important parameters, like water hardness and the calcium to magnesium ratio. You can see that the waters in groups C and D have the highest hardness, but groups A and B are close to the post-treated desalinated water produced by the desalination plants. A necessary level of hardness in post-treated desalinated water is about 60 to 120 ppm. The medical recommendation to the calcium to magnesium ratio in drinking water is no more than 3. We can see that groups A and B are similar to desalinated water in terms of hardness and the calcium to magnesium ratio, while groups C and D differ. This means that the tap water in groups A and B is a result of intensive desalinated water addition to the network, and the water in groups C and D still contains more water from the Kinneret Lake and/or local wells. The issue with evaluating the potential for iodine deficiency in consumers of desalinated water is that the mineral composition of our tap water is quite unstable. The provider mixes water from different sources on a daily and even hourly basis for technical and economic reasons. We measured the iodine content in the same faucets in two cities over 24 hours and observed a fluctuation of from 20 to 56% as a coefficient of variation. The concentration measured over 3 years in the very same faucet showed a fluctuation of 151%. We observed similar instability in the magnesium content of tap water in our previous observation. However, as you can see, despite this fluctuation in iodine concentration, it is always very low, which should be a public health concern. And the conclusions of our work are the following. Adding ADTA to the alkaline matrix in a 1:1 molar ratio to the calcium plus magnesium content, or at least 0.1% ADTA, prevents clogging of the ICP-MS nebulizer by precipitated carbonates. The limit of quantitation of the method developed is less than 0.1 microgram per liter, or even better, 0.04 micrograms per liter, if only concentrations less than 1 microgram per liter are analyzed and memory effect is not an issue. Total iodine is stable in drinking water samples for at least 2 weeks at 4 degrees Celsius or at room temperature. The iodine content in Israeli tap water is generally low due to the widespread use of desalinated water, which may lead to iodine deficiency in consumers. I would like to thank my colleagues who participated in this study. Orit Gal, the department head, Yuliana Andrющенko, the lab engineer, and Professor Yona Han, my scientific mentor. Based on the material reported, we have published one article in the Journal of Food Composition and Analysis this year, and the other article is forthcoming. So, thank you very much for your attention, and we'll see you on our next lecture. Goodbye.